Hello students, welcome back. Let us resume our discussion in section 1, rank and determinants. In the previous video, we went through what it means by determinants in section 0, and then in section 1.0, subsection 1.0, we reviewed the concept of the rank of matrix. Okay, alright, now we are ready to go on to theorem 1.1, and here it is. Let A1, A2, A3, and so on be column vectors of an n by n matrix A. Then we have this equivalence. The column vectors A1, A2, A3, and so on all the way over to AN are linearly independent if and only if the determinant of the original square matrix A is non-zero. Equivalently speaking, the column vectors A1 through AN are linearly dependent if and only if the determinant of A is zero. The equivalence between these two is easy to see, so I'm going to leave that to students. A little bit harder to see is this step. This is equivalent to these two together. Let's see, how about the first line? A1 through AN are linearly independent, then determinant is non-zero, so that's the one direction, the forward direction of the first statement. How about the backwards? If the determinant is non-zero, then these are linearly independent. Instead of that, we can take contrapositive. We assume from here A1 through AN are linearly dependent now. We took the negation. Then determinant is zero. We took the negation. So that's a contrapositive of the backward direction. Now, there may be some students who didn't take the Intro to Proof Math 3320. In that case, you may not understand the concept of contrapositive yet. In that case, you can reason like this. The column vectors A1 through AN are either linearly dependent or independent, not both and nothing else. Likewise, determinant of A is either 0 or non-zero, nothing else, and not both. So because of this dichotomy, once you have a equivalent statement, we can consider linear independence case, first case, and the other case, linearly dependent case. And then use your reasoning. Independent, then determinant is zero, non-zero, the straighter forward direction. Now how about the other? Linearly dependent, then let's look at the other. Determinant is equal to zero. So we just took first half of this and first half of that and put those together. Did we exhaust all possibilities? And yes, we did, because of this clear dichotomy. We have to have linearly dependence or independence, nothing else. So dependence or independence, nothing else, no both. Likewise, determinant is zero or otherwise non-zero, nothing else, and certainly not both. So we covered, and that's it. Okay, all right. Now, let's go to the second implication. That's a bit easier. A1 through AN are linearly dependent. Then we have to prove the determinant is equal to 0. How do we do that? First, we're going to assume these are linearly dependent, which means if I get a linear combination equals to 0, then this is what it means by linearly independent. If you have a linear combination equal to 0, then all xi is equal to 0. Now we are talking about linear dependence, right? So we have to negate. Not all xi is equal to 0. Previously linearly independent, so the conclusion was all xi was equal to 0. Now linear dependence, not all. So that means there's at least one non-zero element. And that's what this one is. At least one, there is some non-zero coefficient. There can be 2, there can be 15, there can be 100, but there should be at least one. Okay, we got one. Now, xi is non-zero, so we can solve for ai, but that's a bit cumbersome. So let's use a bit of a simplification here. Without loss of generality, we can assume x1 is not equal to 0. How? We can simply rename it. If x5 is non-zero, okay, then we call x1 is x5 and vice versa, and a1 is a5 and vice versa, and then simply go from there. Consequently, we can assume x1 is non-zero, and we can solve for a1. This kind of trick, very, very typical, without loss of generality, and then we can push everything to either first or sometimes to the last. Okay, let's solve for a1. So push everything to the other side, so we have a bunch of negatives. And then the key step, divide by x1. Can we divide by x1? Yes, we can, because x1 is non-zero. Now, if you don't want to use this without loss of generality, then you can solve for ai and then divide by xi. Yeah, you can do that. It's just that right-hand side is a heck of a lot more complicated because we have all these negatives and sums, and then except for ith term, things like those. Okay, now that we have a1 is a linear combination resolved, how do we use it? If you plug it back in here, then you're not going to get anything because this came from this by solving. So if you plug it back in, then you're going to get something trivial. 0 equal to 0 is not helping. So where do I plug this in? What do you want to prove? This is what you want to prove. So you're going to plug it into the determinant right here. So let's do it. Determinant of A is determinant of A1, A2, A3, all those columns put together. And the first column can be rewritten as this linear combination. And then we can use the property of the determinant, multilinear. So this linear combination can be separated like this. First coefficient out, and then A2. Next coefficient out, and then A3. The next combination out, and then we have a4 and so on, and the last coefficient out, and we have an. So what do we have? We have a bunch of determinants with at least one duplicate column, a2, a2, or a3, a3, a4, a4, and so on and so forth. In the end, an. They're all zeros because of the alternating properties. So what do we have? Adding a bunch of zeros, we get 0. Determinant of A is, therefore, 0. That completes the proof. So here we go. Let's assume linear dependence. So we have a linear combination, x1, a1, x2, a2, and so on, plus xn, an is equal to 0. However, not all the coefficient is equal to 0. And then solve ai without loss of generality, solve for a1 dividing by x1, and then plug those into the determinant. And then we can use multilinearity and alternating property to reduce this into 0. Alright, that completed the proof of the second statement, and let's go to the first statement. This is going to be a bit harder. Let's go. A1 through an are linearly independent. Therefore, they must form a basis of our n. We have n linearly independent vectors in an n-dimensional space. They must form a basis. Therefore, they generate all the vectors in Rn. In particular, they're going to generate the standard basis vectors E1, E2, E3 all the way over to En. By the way, all these are column vectors. Alright, how do I write this? Generate by A1 through AN. That means E1 can be written as a linear combination of A1 through AN. E2 is a linear combination of A1 through AN, and so on and so forth. In the end, En is also a linear combination of A1, A2, and so on. So we have N linear combination equals to E1, E2, E3, like this. In short, we have a system of linear equations. Looks like we have an N system of linear equations, but there's a problem. These are not x1, x2, x3, and so on. These are, by themselves, column vectors. So each line is, as a matter of fact, a vector equation of dimension n. So each line is a system of n linear equation. And we have n such things. So this is n systems of n linear equations. It's enormous. So n by n times n. So this is going to be n squared. That's going to be a matrix equation. In the end, yes, it'll turn out that way. If we put together all those columns, A1, A2, A3, and so on, then you're going to get the square matrix A. And then if you put together standard basis vectors, E1, E2, E3, and so on, all the way up to En, as columns, then I'm going to get the identity matrix. How about the middle? That's a tricky part, but assume we did it. Assume somehow we got it done. Then we're going to end up with this matrix equation, A times B is equal to I. Now we are in business because we can use the multiplicative property of the determinant. Determinant of A times determinant of B is equal to determinant of AB. But what's AB? AB is equal to I, and the determinant of I is 1. So conclusion, determinant of A times something is 1. Therefore, determinant of A cannot be 0. So we got everything here except one big hole, of course, which we will fill up. Assuming A1 through AN are linearly independent, there are n linearly independent vectors in an n-dimensional space, so they form a basis, so they generate. In particular, they generate standard basis vectors, E1, E2, E3, all the way over to En, and that's what this is. E1 is a linear combination of A1 through AN, E2 is a linear combination of A1 through AN, and so on. Somehow from here, you have to get this. Putting A1 through AN together, we get square matrix A, and then square matrix of B somehow is equal to square matrix I by putting together E1, E2 all the way over to En, and the conclusion follows. Alright, let's fill up this big hole. How do I get this matrix B? Okay, here we go. In this system, look at the first row and take the coefficients and then arrange them as not rows but as a column. Second row, we have all these coefficients, B12, B22, and so on. Arrange them as a column. And so on and so forth. This one, arrange as column. So we're taking each row into column and then forming column vectors, B1, B2, and so on. Does it help? Yes, it does, and here we go. This is a system, that's where we begin. And please note that each A1, A2, these are all column vectors. A1 is column vector, A2 is this red column vector, and so on. This AN is this green column vector, and E1 is this column vector. In short, this first line is equivalent to this column vector equation. Similarly, this one is equivalent to the second equation, and so on, and the last one is equivalent to the last line. Now, let's look at the first equation here. It is possible to put those A's together into a matrix A like this, and then get all those coefficients together as a column vector, and then the right hand side. This matrix equation will turn out to be equivalent to this vector equation. Can we check? Let's see, how about the first line? First line is B11 times A11, B21 times A12, and so on, plus Bn1 times A1n. And look at this. First row times this column dot product. That's precisely what you saw in the left-hand side here. And that's equal to 1. Same. Do the same thing to the second line. A21 times B11, A22 times B21, and so on. A2n times Bn1 is equal to 0. How about this? Second row times this column, dot product, and equal to 0. Precisely the same. So this matrix equation is equivalent to this column vector equation, and in turn that's equivalent to the first line. Same for the second line, third line, fourth line, all the way up to nth line. So what do you have? We have matrix A times column vector, matrix A times column vector B2, matrix X times column vector Bn, kind of like this. And putting all those together, we get this matrix equation. A part is common, exactly the same, so no problem there. And then times this column vector B1 is equal to the column vector E1. And this A times column vector V2, this B2, is equal to column vector E2, and E2 is here, and so on and so forth. So yes, it turns out A times B is equal to I, and from there, proving determinant of A is non-zero is not difficult. So that completes the proof, and as for following all those indices, good luck. I don't think even I can reproduce this thing out of complete nowhere. I have to really take time, get all those indices together, check and recheck, test it, and then I can explain. So that's the expectation I have from you. I'm not asking you to produce this thing out of nowhere. My goal is, when presented, you understand. Okay, alright, so much for theorem 1.1, and let's go to a little bit more useful results. And here we go. Determinant of A is non-zero if and only if the inverse matrix exists. So invertibility and determinants non-zero, they are equivalent. How do you prove that? The first part, determinant is non-zero, then that's equivalent to A1 through AN are linearly independent, which is theorem 1.1. And then in the proof of theorem 1.1, we did get this A times B is equal to I. Do you remember? The difficult part. You see, this part. In the end, we got A times B is equal to I, and that B is the inverse matrix. And remember, it was quite tricky to define B's and get a B. That was because it was inverse matrix, and inverse matrices are always difficult to find out. So there goes one direction. How about the other direction? If A inverse exists, then it is easy to prove that determinant A is non-zero simply by the multiplicative property of the determinants. Determinant of A times determinant of A inverse is determinant of identity matrix, which is 1, so determinant of A should not be 0. Let's see, do we have time for this one? Determinant and rank. This is a one-liner as well. Determinant is non-zero. That means, as we saw in theorem 1.1, the column space has dimension n. All these are linearly independent. And that's equivalent to rank n. So yes, these are equivalent. That completes section 1.